manufacturing of advanced composites, and it's basically the idea is a new paradigm for advanced composite structures. I'm going to do a little history. Let me get my pointer here. A little history of AM processes with a focus on composites, and where we are at today and what the future holds for us. So back in the late 70s, early 80s, I was electrical engineer working in robotics research and at Rensselaer Polytechnic Institute. And Sikorsky came to us and wanted us to know if we could use robots to make composites. And I didn't know anything about composites, and it was a love affair. I couldn't believe the technology that the capabilities of composites. The processes were awful. So it was all manual layup and little fire replacement at that point. And so we spun off a company called Automated Dynamics, and my dream was to be able to design a really cool composite part, push print, and get a part. And I'm happy to say that after 40 plus years, we've made some progress here. So this is Michael Emons. He's a managing partner at AZL Aachen and also the managing partner for Accountability. And I just love this analogy that he has between writing and composites. So in the early days, handwriting, hand layup, this is what I discovered. The thermoset hand layup in the early 80s, and I thought, wow, there's got to be a better way than this. It was awful. So probably the best invention ever was the letterpress, which is just simply a wine press and movable type, and it transformed the world. And similarly for composites, it's manipulator based, automated manipulation of the composites to make a structure. And then flatbed plotters or printers, you can with your computer, write a book and or write a paper and have it printed. Likewise, we can now print simple composite structures with automated fire replacement and especially thermoplastics. I quickly realized that thermoplastics were the future back in the 80s, and I'm happy that the rest of the world is finally agreeing. I think I heard a moan there. And nowadays, if you've ever seen a modern printing operation, it's phenomenal. You design a composite or a magazine, a book, or a newspaper, and you basically push print, and truckloads of printed materials come out. Like, for example, one of my favorite journals here, Composite World, a little fuzzy background. But it's even has my name on it. It's all printed, all automatic, and that's where we're headed with composites. That's the gist of this presentation. Is right now we're in the stage where we can digitally print additive manufacture parts, and now we're moving into integrated fabrication of completed structures. A little history of additive manufacturing. I don't want to bore you here. These are the 6 original additive manufacturing technologies. I actually played a role in the material jetting and directed energy back in the 80s, anyhow. And these are the original patents from that time. I was working on this. I got an NSF grant to develop what's now called direct jetting. And I was doing a presentation at a conference, and this guy, Bill Masters, walked up to me and said, "That's interesting. I have a patent on that." And he did. It was, it's amazing. So this is the original patent for what we now call 3D printing or additive manufacturing. And these are the other technologies. Chuck Hull of 3D Systems with SLA, Carl Deckard with SLS, which was later acquired by Desktop by 3D Systems. And Bill Masters invented fused filament fabrication. So you'll notice a theme here, Bill Masters. So Bill and I are still friends today. I handed over all my technology from this direct jetting, which I call BPM, and he named a company BPM and actually built and sold printers. It's no longer in business. And he also invented FFF, which fused filament fabrication. A lot of people think that Scott Crump invented, including Scott Crump, thinks that Stratasys invented FDM. It's the reason why Stratasys says FDM and everybody else says FFF is because Stratasys trademarked fused deposition modeling. It's the same technology. It's melting a filament and creating 3D structures with it. So by any measure, Bill is the inventor of additive manufacturing, and Wikipedia just recently corrected that. Bill also invented the modern kayak. He just sold a couple of years ago his Perception and Aquaterra kayak companies. So then the last historical 3D printing technology is binder jetting. Ellie Sachs of MIT just simply combined material jetting and powder bed fusion. Simply, I say, but it was a major. I thought it was genius. He just combined these two technologies to solve problems with throughput and different materials. You can, with binder jetting, you do everything from ceramics to polymers, metals. It just requires a secondary sintering step. You bind the powders together, and then you remove the unbound powder and sinter it. So you'll notice that it's not exactly push, print, get part. There's post processes, and so be it. It's still additive manufacturing. So Ali also co-founded Desktop Metal, which I'll get to in a minute. And if you're following the news, this Desktop Metal has a $750 million market cap, and they're being acquired by Stratasys for $1.8 billion. And their EBITDA is minus. So something I don't understand here, but it's a huge buyout. So now we go into where we're at today with additive manufacturing of composites. Despite all the limitations that I saw early on, this industry is just exploding. It's growing at over 20% per year. It's a $20 billion business right now. However, it has problems. No fiber, poor Z-axis strength, relatively low throughput, warping voids. But despite all that, it's growing exponentially. So when I first saw composites, like I said, I was astounded. I worked in metals. This is a normalized specific strength and stiffness for compared to 4340 steel. So this is a very high quality steel, and we'll set that value at 1, and then we can easily compare other materials to it. When I do this kind of a thing for a less sophisticated audience, I do a bar graph, and the last one shoots off the page for dramatic effect, but you won't be impressed with that. But I just love this, showing people how strong these materials, how strong and stiff these materials are compared to legacy materials. 4340 steel, you want to build an airplane, make it out of aluminum, at least up until now. This is 7075 T6, so much higher specific strength, but still about the same modulus. PEEK is a high performance polymer. It's amazingly strong, but not very stiff. Add a couple fibers to it, add a little bit of chopped fiber to it, and now you're better than metals in specific strength and stiffness. That's just amazing to me. Even low tech, polypropylene e-glass, like low fiber volume, continuous fiber, inexpensive, dollars per pound, polypropylene e-glass is amazingly strong, not that stiff, but so start adding carbon fiber to it. This is what Mark forged with a low percentage carbon fiber in nylon, it gets significantly better properties. And now we move into the what we're continuous fiber reinforced material. This is a representative of the DM fiber printer is representative of desktop composite manufacturing, additive manufacturing. So, needless to say, these materials are amazing. Greg Mark was the first to introduce a fiber printer. Like I said, it's very low fiber volume. It has very, very long minimum fiber length, and you can see us composite people understand that this isn't a very pretty composites, but it's better than plain polymer or even chopped fiber. So Arrivo started making real in situ consolidated printers, and it was originally founded by Hermann Beta, but Sony View bought a Silicon Valley venture capitalist bought them. They originally sold work cells, and now they only sell parts. They basically make bicycles with this technology. They stole one of my engineers, and he designed a little mini in situ consolidation head with laser heating, and built these little work cells with a robotic arm. And they can't make these bicycles fast enough. I'm told that they have 72 of these work cells making bicycles in Vietnam, and they're expanding into other countries now. It's just amazing to me. I'm not very enamored with this e-bike here, but I kind of like this design. So 3D printed frame, and this one has a 3D printed wheels on it too. So Riley spun off from Arrivo with an idea that he had, which is basically you take a pultruded thermoplastic pultruded composite rod, heat it, bend it, and then drop the pieces in with the robot, drop the pieces into a mold, and then mold it into a final shape. You can get very good properties with this because you can get the fibers through the joints. But again, it's a secondary process. It's additive manufacturing, but you're including a molding step in here. Nonetheless, you get very impressive material properties, or parts from lightweight parts. And Isoprint, they're based in Luxembourg, and they started with really advanced FFF fiber reinforced printing in 3 dimensions, but now mostly they just sell 2D layered printers. They weren't making as much money with this technology as they are with this technology, so they're selling more or less printers, but continuous fiber though. They do have continuous fiber capability. So Desktop Metal, this is Eli Sachs company. He was a co-founder with Rick Fulop, and they do mainly binder jetting, but they acquired a company called Make Composites that Konstantin Fetfadis created, and Konstantin helped them to build this printer, which we own one of these at Albany, TSS Albany, formerly Automated Dynamics, and it has interchangeable heads. You can print FFF filaments, chopped fiber, or continuous fiber. It has like a mini fiber replacement head, so it will print flat laminates anyhow with advanced composites. And this is Konstantin here. He's been a friend of mine for many years, former SAMPE Young Professional of the Year. He left Desktop Metal. I'm going to just go back here for a minute. You'll notice that Rick is advertising his fiber printer, but he's holding a metal part here. Kind of tells you where his head's at, right? So Konstantin wasn't happy with that metalhead attitude, and went off and joined 9T Labs. 9T Labs has a technology they call additive fusion, which they print they can print continuous fibers, and then they take those fibers and then drop them into a mold, and you can mold complex shapes by putting multiple continuous fiber composites into it. It's very clever, actually. Like this bracket here, they mold these individual little pieces, put them in the mold, and then drop BMC in. And when the BMC gets compressed into these crevices, it pushes the continuous fibers in to get continuous fiber reinforcement in the structure. I think it's very clever. Constantine is North American president. He runs a lab and development center out of Lowell, Mass. So they basically, they call it additive fusion. It's printing and then a fusion process, and they only sell equipment, but they do it on a consignment basis, where they help you with the process. Orbital is FFF printing, co-extrusion. Basically, he puts fiber through the middle of a FFF head and then co-extrudes thermoplastic around it. Very artful designed machines. There was a news release just yesterday. He has signed a $1.7 million contract with the Space Force to build antennas using this technology in space. Cole is a real space cadet. I'm sure you've seen him if you've been to a conference, because he goes to all the conferences. So it is basically just co-extrusion FFF, though. Electro Impact with their Scram machine, scalable composite robotic additive manufacturing, is taking the basic FFF technology and integrating it with an in situ consolidation head. So this head has two FFF extruders and one continuous fiber in situ consolidation head with laser heating. So this is a printing with PLA, extruding the mandrel, and then in situ consolidating the composite fiber peak, carbon fiber peak structure over it, and then you can wash the PLA out. And they're in the process now of upgrading this to with a metal additive. So this is a Meltio system. It's a wire arc additive manufacturing head, but it's different. It's different than, it's like a MIG welder, but it's uses laser heat instead of electrical arc. So they're integrating the FFF with the in situ consolidation with metal additive and finished machining. So this is the way the industry is heading, is not just single process, integrated processes. In this case, it's all in one single work cell. I'm only going to do one of these chop fiber and printers for brevity here, but they also, CEAD also has a advanced tape placement system that they can integrate into these pellet extruders that they're making. Chopped fiber pellet extruders. They claim this is the world's largest printer that they're installing right now in the Alcere Marine facility. It's on the scale of the Ingersoll machine, and it may be actually biggest by volume, but they also have the option to print continuous fibers with this machine. And now we're in situ consolidation. This is the technology that I helped to develop back in the 80s. Basically, you use laser. Well, it started with hot gas, but now we use laser heating to melt the thermoplastic tape, and then the robots to consolidate it on complex structures without an autoclave. A little brief history of automated dynamics. Now TSS Albany. We were acquired by Trelleborg, I don't know, four years ago or so. At RPI, we were using film fly winding. Basically, what we did is we took a fly winder and with thermosets wound complex shapes, very similar to what MF Tech is doing today. And MF Tech was acquired by Coriolis, but basically a robotic filament winder. I quickly realized that thermoplastics were the future and built a prototype development system with hot gas heat for in situ consolidation of thermoplastic composites. We sold our first machine to ICI Fiberite. I have a hat from that era. David Leach was working in the building next door at Fiberite, and this is ICI Composite Structures in Tempe, Arizona. And we actually bought ICI exited the business, and Automated Dynamics bought this machine back, and it still operates today with upgraded controls, but this machine is still operating. We sold the first articulated arm robot to NASA in '89, and I developed the laser heating technology in 2014, and now our current head, this is a 2 kilowatt laser, and now we have our current head has 2 3 kilowatt lasers on it, one for the substrate and one for the incoming tape for improved control and greater throughput. So that's a brief history of automated dynamics. I'm not going to bore you with all the marketing stuff about what we do at Automated Dynamics or TSS Albany, but everything we do is in situ consolidation. We don't do any other process other than thermoplastic in situ consolidation, including fuselage structures where we fiber place the frames and stringers, assemble them into the mold, and then in situ consolidate the skin over the outside to co-bond it into a complete fuselage structure. Or what other structures, like for example, this is a floor panel for a helicopter. We do drive shafts, all kinds of stuff, and including a rail gun that we've been making for the Navy, which has over a ton of IM7 peak on it. And you just can't make a structure like this with any other technology other than in situ consolidation, because it's a really thick wall structure. You get no marcelling, and you can build it up one layer at a time and very easily. So like I said, everything we do at Automated Dynamics to TSS Albany is in situ consolidation, including these e-glass polypropylene pressure vessels. We sell these by the hundreds. Various structures. If you ever see pipes by the side of the road with these bands on it, that's our technology. It's putting those reinforcement bands on, which that little band of e-glass polyethylene increases the pressure rating of that pipe by a factor of 3. So Albany is not the only game in town now. A lot of people are doing in situ consolidation, AFPT, Coriolis, Microsam, Conbility, Electroimpact. I'll get into these in more detail. So Koch saw what they were doing at Boeing St. Louis and went back and with help from Fraunhofer developed a technology to laser in situ consolidate thermoplastic composites, and he's doing a lot of work right now in everything from pressure vessels to this machine here. I'm not going to show you this whole video, but this machine fiber places in situ consolidates a tube, extracts the tube and cuts it into little cylinders that are used for rotor overwinds or rotor sleeves for high-speed electric motors, all automatic. It's multi-process. It's not just fiber placement. It's not just in situ consolidation. It's an integrated work cell that makes parts for electric motors. We probably all know John Mullally. He's now the U.S. sales rep for Microsam. They have been doing all kinds of things, including in situ consolidation. They started with film and winding. They make pretty much everything in the composites world right now. There's a nice article in Composites World about this beam that they made for the multifunctional fuselage demonstrator for Airbus, and including toolless manufacturing. You can make structures without a tool by using one robot as the tool and the other robot as the fiber placement technology, and they do complete automated work cells. This is basically a lights out COPV manufacturing facility where everything is automated, and Roth sells something very similar to this. Electro Impact has gone big. Everything they do is big. This is I think 14-toe in situ consolidation head that they developed using a variable spot size laser. So besides these massive thermoset machines, they also have thermoplastics besides the SCRAM technology that I just showed you. Broche is another company that's integrating fiber placement into work cells. This is a completely automated work cell that's making parts for aircraft. They have work cells and completely automated factories. And the new kid on the block is Add Composites. I would suggest that you go to his website. He has a really excellent learning center. He puts a lot of work into teaching others about composites, and especially fiber placement and in situ consolidation. He's using a Hum3 Heraeus heat source here. It's a visible light rather than laser. The advantage is that you don't need a class 4 laser environment. You can do in situ consolidation without a class 4 enclosure. So where are we headed from there? Very quickly, this is the Collins view. Next steps are automated fiber replacement, welding of structures together, automation of the whole process. This is Airbus's vision here, and if you want to know about that, read Ginger Gardner's article in this month's Composite World. She has an awesome article about this technology. She really outdid herself, explaining all the different technologies that they're using in this multifunction Clean Sky 2 multifunction fuselage demonstrator. This is the upper fuselage of that, which Ginger's article explains really clearly. It's an in situ consolidated skins, and then they ultrasonically tack and ultrasonically bond the stringers in, and then resistance bond the frames. So it's all automatic. This is where this is heading. Like, this whole process can be automated now. It's not just fiber placement, not just in situ consolidation. It's automated manufacturing of the entire fuselage structure. I'm convinced that this is what the next narrow body jet's gonna look like. It's gonna have some of these technologies integrated together to make an autoclave, no rivets or minimum rivets, thermoplastic composite structure. You can see these videos on YouTube. It's worth watching. This is an airborne, completely automated manufacturing line. It's stamping, but it's fully automated. I would contend that this is additive manufacturing. It's lights out, make the whole structure automatically, and all you got to do to change the part is change the molds and the program, right? So I think that's auto manufacturing. Now back to Michael Eamons. This is his Conbility ultra fast consolidator line. He basically has separated the operations into a continuous process. So it very rapidly makes an entire structure starting with in situ consolidation and then stamping. So in summary, the additive manufacturing of advanced composites has gone from small structures to large structures, and now we're in the tipping point of going from single processes to integrated manufacturing processes for complete composite structures. And I even made the timeline. So we have time for questions, a couple of minutes for questions if you have any.
Yeah, great. Thanks. Thanks, David. Excellent presentation. Really great. Any questions, either if folks want to shout up or raise your hand, either way? I guess I'll jump in with one, David. One of the challenges I think with thermoplastic kind of additive in situ is both the kind of lay down or deposition rates to get full consolidation, and then for any of the semi-crystalline polymers, controlling the cooling. Do you think we'll always need to go through like a secondary operation to get to decent rates and full consolidation, or do you think we can achieve full in situ?
Well, we do full in situ every day for everything we do at TSS Albany. However, there is a knockdown. We are currently not getting, well, at least for high performance polymers like PEEK, we are not, and no one else is either, getting full consolidation. So it's more like 70-80% of interlaminar shear at reasonable rates. And you can get low enough voids for aerospace, but the main problem and the crystallinity can be dealt with also. We do what we call ghost passes, or you can go over the structure later with a laser at lower speeds and raise the temperature up to the crystallization temperature. There's actually a benefit in that because people don't realize this, but about half the shrinkage of a thermoplastic composite is a crystalline thermoplastic composite is the crystallinity. A lot of the shrinkage occurs in crystallization, not just CTE. So by crystallizing later, even with the oven post process, you reduce that warping effect.
Yeah, right.
So I'm in the middle of trying to develop the next generation of technologies to overcome these limitations.
Yeah, great, thanks. So I see a few questions popping up here. I think Susan was first.
Yes, way back at the beginning of your presentation, you had a chart that showed specific strength and specific modulus for the composite. Yeah. Is that unidirectional or was that?
That's uni. That's okay. Uni. Yeah, okay. I'm cheating. Okay, so no, if you want to, I sometimes I should have added that actually for this group, but I sometimes include black aluminum, right? Yeah. Which just knock it down by a half, basically. That's a good question.
Wanted to be clear.
Yeah.
And then I think Mike was next. Mike Buck.
Yeah, Dave. Great presentation. Thank you. I had a quick question on the in situ consolidation process. You talked about the wide body, or the small body, I should say, aircraft as part of your presentation. I know a lot of folks have been looking at a two-step out of autoclave type process where they'll use a rapid lay down of material but not fully consolidated, and then follow that up with an out of autoclave or an oven consolidation. What are your thoughts as far as, in situ consolidation would be best, but it's slower. What's your thoughts as far as how that's going to finally shake out?
I believe that unless I can make some of my ideas reality, that it will be a secondary process. You know, you're not gonna fly an airplane that's 80% of the properties. When you can oven consolidate it, it won't be autoclave though. I believe that like the bottom half of the multi-function fuselage demonstrator is that it's rapidly laid up and then oven consolidated. I believe that's probably what's going to happen for the next generation.
Thanks.
And Dipper, you have a question?
Yeah, thank you. Thank you for the excellent presentation. I just have one question, like there will be a crystallinity variation across the structure or a crystallinity gradient. Is there any way to measure that and how that is going to impact the final performance of the part?
The thermal gradient across the structure?
The crystallinity gradient, the crystallinity development.
Oh,
yeah.
Yes, that can be measured with a DSC or not? Yeah, DSC. By sectioning it, and we, it's not difficult to get full crystallinity with this technology. If you're gonna go really fast, you're not gonna get full crystallinity. You have to go back and either oven crystallize or do subsequent passes with the laser to heat through the thickness to get the crystallinity.
Okay, thank you.
Yeah, we got maybe it's time for one more. I see Alberto, you've got a question.
Yeah, I was going to ask about on that in situ consolidation. When the thickness is low to 20, 30, 40 layers for some structural parts, that crystallinity develops through the core the same way, or the oven curing can deal with that?
Yeah, the oven, both. Like for example, the rail gun is hundreds of layers thick. What happens is it doesn't consolidate in the you don't get full crystallinity in the layer that you're placing, right? You don't, but the it reaches crystallinity temperature several layers down. So each pass you're crystallizing more and more, right? So you can get full crystallinity.
Okay.
Or you can put it in an oven.
All right. Well, thanks. I know we're right at time. I'm sure David is available if anybody wants to contact him by email and so on. David, maybe if it's okay, we put your email address in the notes from the meeting if anyone wants to follow up with you.
Sure, I'm perfectly okay with that.
Great.
Oh,
thanks.
I should have mentioned that this presentation, everything I said today is me, not Trelleborg. Okay, they're not responsible for me. This is statements that I have made, and it doesn't reflect anything that Trelleborg's doing.
Yeah, great. Well, as we mentioned, our next meeting is August the 16th, which again will have a feature presentation, and also don't forget the TC webinar, SAMPE TC webinar series on July 27th with Steve Nollet and Alberto on wind power activities as well. Okay, so thanks everyone. We're right at time, so we'll hopefully talk to everyone next month. And thanks again, David, for the presentation.
Thanks, everyone.